All right, scholars, another friction and work example smushed together. Now, this is another one where we're going to incorporate the work kinetic energy theorem. It's not exactly obvious at first that that's what we should be doing. But just like we did in the last one, we're going to start with a picture. We're going to write down everything we know, and we're just going to see where that takes us. So let me read it. We'll take a moment to pause. We'll draw it out, and we'll get going from there. So it says, a skier traveling 12.0 meters per second reaches the foot of a steady upward 18-degree incline and glides 12.2 meters up along this slope before coming to rest. What was the average coefficient of friction? So let's take a moment. I'm going to pause, see if you can draw this scenario, label whatever you can, draw any free body diagrams we might need, see how far you can get, and then when you unpause, let's compare that to what I've got. All right, scholars. So here's what I've got. I've got a very poorly drawn skier who started at 12 meters per second. By the time they get to their maximum height up the hill, their final velocity is 0 meters per second. They've stopped. They go 12.2 meters up the hill. The angle of the hill, 18 degrees. In a moment, we're going to end up having to break this into components. We're going to have to do that whole thing with the incline, which is a little tricky. I'll admit, a little tricky. That's okay. We'll get to that in just a moment. I've also written down some of those equations we used last time. Work kinetic energy, frictional force, net work. We've kind of got all of our pieces in order. Remember what we did before when we were on an incline. It's going to make our life easier if we treat the incline like it's flat ground. So I'm going to say the incline is the x-axis. Straight up from there, I've drawn that somewhat poorly. Straight up from there, we're going to call that the y-axis. That's a little better. And that gives us some advantages, which we'll see in just a moment. So the main reason we want to do that is because if we draw, I'm going to redraw the free body diagram in a second, but if we include our forces here, we've got the normal force. Remember, normal force is always perpendicular to whatever surface you are resting on. So it is pointing off at 18 degrees like so. Here is the weight of our skier. Let me add that. That's our normal force. And then, of course, the thing that is slowing the skier down, there's two things. There is a component of gravity. If we drop this down, so we've got our gravity acting straight down. You can show with similar triangles that this angle is the same angle. And so what we have, I didn't draw that very well, are two little triangles. One of the triangles is exactly opposite of the normal force, and you can show that that is mg cos theta. If you don't trust me, we've got our adjacent, which would be this leg here, over the hypotenuse. You can show with a little trig that this is mg cos theta. That means that this one's going to be mg sine theta. So I didn't draw this very well, and my apologies for that. There we go. That's a little bit better. So you've got a weight, the component that's sort of modified by sine theta, acting down the ramp. You've got this weight in the cosine direction that's opposite the normal force, so that's going to be important. And then finally, it didn't tell us it was frictionless. In fact, it asked for the coefficient of friction, so we need to add on here the force of friction. So I will admit this is the most complicated free body diagram that we've seen before. So what I'm going to do, let's break that out down here so that you can see it. I'm going to take a moment and do the free body diagram. See if you can pause and also write it down. I'm going to rearrange it now so that y and x are in their sort of normal orientation. Okay, so we are going to take just the components here. We're actually going to leave out our big mg for reasons that might become clear in a moment. So I've got the easy ones. You've got straight up and down in our weird new rotated coordinate system where y is up like that. You've got normal force straight up. You've got mg straight down, mg cos theta, pardon me, straight down. And then acting in what is our new x direction, down the slope, you've got two forces, the force of friction and the weight along the incline, which makes sense if you back up for just a moment. The two things slowing them down are, and I'll label them here, the force of friction acting down the hill, and mg sine theta, which also acts down the hill. Now, because we're going to end up not needing it, mg, just the weight itself is not really acting in either the x and the y. I'm going to opt to leave that off of my free body diagram so as not to confuse you. Let's see where we can go from there. So I promise we're going to use the work kinetic energy theorem, but for right now, we've got our free body diagram. We might as well set up Newton's second law. And because we've got x and y, we need to do the net forces in the y direction and the net forces in the x direction. Now, because we've rotated our coordinate axis, this makes life easy for us. The normal force is acting up in the y direction. The weight force, mg cos theta, is acting down. So this would be n minus mg cos theta equals ma in the y direction. Now, the way that we've oriented our system, it is not accelerating in the y direction. It is only accelerating downward on the incline. It's slowing down through the incline. So let's go ahead and just get that set up. That means that this is 0 y acceleration, which means this is 0 n minus mg cos theta. So of course the normal force is equal to this weight component. N is equal to mg cos theta. Let's set up this one. Let's see what happens. You're going to see that it's not very nice. But what we've got are frictional forces and the weight in the moderated by sine theta acting in the x direction. Let's call that negative for reasons we'll speak about in just a moment. It's acting opposite the motion of the person. That's mostly why we want to do that. So we might go minus f of friction minus mg sine theta equals ma in the x direction. Now, truthfully, we did not need to do this. If you kept going, you'd get to a point where you would sort of run out of room. You'd end up with you're trying to find coefficient of friction, you need speed, and you've got acceleration. It becomes a whole disaster. The next thing we might think to try is the work kinetic energy theorem. And I'm just going to kind of tell you, this is usually best for a one-dimensional application. What I mean to say is that the net work done on something in a forward or backwards direction, or something along those lines, it's going to be best to use this. Now, even though we get tricky and cute with our axis, really this is a two-dimensional problem. The person is both moving and going up. So in fact, we kind of want to put several ideas together. I think the best way to address this question, once we've gotten to this stage, we have lots of information written down, I think the best approach here is actually to use energy conservation. So check this out. Let's think about this situation from a very conceptual standpoint. Let's think energy pi. So go back to here. The person has not yet made it up the incline. What type of energy do they have? Well, they're just moving. It's just on flat ground, and we can assume for right now that there's no friction. It actually doesn't matter because we just care about their kinetic energy the moment before they hit the hill. So with that in mind, this is purely 100% genuine kinetic energy. When this person has made it to the top, remember, energy can't be created or destroyed. Instead, this kinetic energy, we have the same size. I'm going to try to draw it well. That is an ugly looking pi. Same size pi, and it can get split into two things. They've gone up, so they've gained potential. Let's say that this little section here is potential. And then the remaining work, like they would have gone higher if there wasn't friction, this is going to be the work done by friction. You can also call that thermal energy. In other words, that's the heat generated by the friction between the skis and the hill. We can take the kinetic energy, put that on one side of the equation. We know that however much kinetic energy there was at the beginning, there's going to be that exact same amount of kinetic energy on the other side. So we don't want to use this. I'm going to very lightly put an X through that because it's not helpful here. This is a two-dimensional application. Instead, energy conservation is going to come to save the day. So on the one side, let's say this is our initial side. We've got just kinetic energy. On the other side, we've got the final potential energy, and we have whatever thermal energy. This is a non-conservative force of friction, removing energy from the system, dissipating it into the snow and the skis. So that will be the potential energy at the top of the hill, plus the work done by friction. Or I called that thermal energy just a moment ago. Those mean exactly the same thing. What we can do now is start to break this out into equations. This will become a little clearer where we need to go, hopefully very shortly. So the initial kinetic energy, 1/2 mv naught squared. We do know the initial velocity, 12, but we actually don't know the mass, which seems like a problem at first, but it's going to end up canceling, just like the last example that we did. Standard mgh final for the potential energy, and then here's where we're really coming down to, do we understand the work done by friction? So work is the parallel force times the displacement. Now we've set this up in a nice way so that the parallel force is just the force done by friction. So we are going to tediously rewrite everything, and we're going to write in, that the force of friction is mu k times n. So that's mu k times n, that's the force due to friction, times d. Now, we did a bunch of hard work earlier. We actually already have the normal force. It is right there. So let's plug that information in as well. We actually need to pause for a moment. As I pause, I just noticed two things that we need to correct, make sure we are good on. So first of all, a moment ago, we had our free body diagram for the force of friction, and we said that was in the negative direction. We want to make sure we continue to do that. So let's make this actually a negative, right there, perfect. And the other thing I noticed is that this height final here assumes that we know this height, and we don't. So we need to figure that out. That is the opposite leg of that right triangle. So opposite over hypotenuse, that's going to be the sine of 18 degrees. That's opposite, the h final, divide by 12.2 meters. So the final height, h final, is going to be 12.2 times sine theta. Okay, that 12.2, by the way, is just the distance that they've slid. So we can, down here, write this as h final is equal to d times sine theta. That makes it a little bit more generic. So I'm going to put that in a box, and then we'll come down and insert that information in here. So I mentioned a moment ago, before my little break, we're going to insert the normal force, we're going to insert the modified height. We'll see where we go from there. Okay, so we started with something that looked very simple. It now looks like a bit of a disaster. One bright spot is that we get to cancel our mass. There's a mass in each term. We don't need it. In fact, we weren't even given it. On the next step, I'm going to do a little bit of cleaning up. Remember, we're trying to solve for the kinetic friction coefficient. So see if you can actually solve for that. I'm going to do most of the algebra on this next pause, and then we'll write down the correct answer. All right, after my hand cramped up, after all this algebra, I've made the appropriate movements. If you need to pause and take a look at what I've done, you're more than welcome to do that. We get here, we have the coefficient of kinetic friction. I've done all of this work. Do be careful. Do not turn that into tangent. That's not going to work like you think it is. And we get here. So when I punch this into my calculator, I get a very confusing answer. I get negative 0.308. Now, that answer is mostly correct. It is between 0 and 1, which is kind of what we expect. It seems a little high for snow, but whatever. The weird thing is that it's negative, and I want to try to explain why that occurred. We were accounting for the work done by friction on the same side as the final potential. So what we're saying here is that that's where this initial energy went. And so when we do that, we're actually already baking in the idea that the energy is being removed from this side, or what you could say is that it sort of started on this side as a negative and we moved it over here. So for that reason, in fact, this should be positive all the way through. There should be a negative sign switch. I'm actually not going to make those edits, just for clarity of the viewer. Let's keep those negative. And what's kind of cool, this is a very, very physics thing to do, is that we can use our intuition. We know that this number should be positive. It came out the correct way. All we've done is make an assumption in the beginning that gave us a negative sign at the end. So the beautiful thing about physics is we can hand wave and say, actually, just kidding, that's a positive coefficient of kinetic friction. So we did a lot. This is a very, very challenging question. I want to point out some conceptual things that are not so challenging. So let's do that. We were asked to find we did an incline problem with friction. But we kind of went back to some basics from the beginning of this unit. We did conservation of energy. We started with some initial kinetic. We ended with some final combination of potential and thermal. Now, depending on your level of comfortability, some of you may have been able to skip straight to this. If not, maybe you need to do this free body diagram. I certainly need to. It's hard for me to skip straight to that solution. Anyway, once we've got all those tools in place, we set this up. We started with some initial. We ended with two other types of energy, thermal energy, or the work done by friction, and potential. From there, it's a matter of inserting all the information that we've got. And after a bunch of algebra, we ended up with a slightly confusing negative answer. Coefficient of frictions tend not to be negative, so we took the positive version because of the way we initially sort of added a negative sign where it didn't need to be. Anyway, if you can handle a question like this on your own with no assistance, kudos. You saw that I made an error, and that's okay. This is a really tricky problem, so give yourself a little bit of credit. If you were able to get through this and feel like you mostly understood it, you are doing a fantastic job. Thanks so much.